As Brian said, I'm Melissa Wilson. I'm with the Ag Nutrient Management Program. I actually was here taking this course last year, so I've been with the program less than a year. What we're going to do today is we're going to start with the basics, some of the natural resources and kind of why we're planting. Next, I'll be talking about basics of soils, and then we'll kind of just progress through more and more complex topics. And then I'll be ending the day tomorrow with how to write a plan, and that's very kind of brief things that you'll need for writing a plan. But we do have an upcoming training, I believe they're September, and both of them in September, right, Trish?
Yes.
For how to write a nutrient management plan. And that will get more into depth about all the things you need, where you can find the information, and stuff like that too. So if you are doing a lot of training and continuing ed for your nutrient management, you'll see a lot of Trish and I. We usually are the people doing some of the education stuff. So with that, we'll go ahead and get started. Basic plan for this segment is going to do water pollution and the water cycle. We'll get into unique challenges for the Chesapeake Bay region because we do have a lot of unique issues specifically here that we'll talk about. Eventually we'll get to a farm nutrient balance, inputs and the outputs, and then we'll talk about some of the best management practices that farmers can use to help reduce some of their nutrient losses. So we'll go ahead and get started off with one of these clicker questions right away. Do any of your personal actions result in the pollution of our waters? Yes is A, and B is no. All right, so the answers will pop up. 92% said yes, 8% said no. So most of you said yes. So let's talk a little bit about that. Now, maybe a long time ago, we could have said that none of our actions resulted in water quality, but these days, with our modern lifestyle here in the U.S., pretty much everything we do is going to impact water in some way. First off, you have to think about intensive crop and animal production. If you eat food that's sold at a store somewhere, like unless you're eating food that's only grown on your property and you're never eating anything else, you're going to have some sort of water quality impact due to the way that our agriculture system here is in the U.S. There's going to be nutrient issues, sediment issues, pathogens, even pharmaceuticals we've been finding in higher and higher levels in our water. So say you do have your own farm, you eat only ever food you produce on your own farm. Well, other things can impact our water quality as well. Urban growth, suburban growth, towns and cities. We all know wastewater treatment plants, right? They have nutrients and pharmaceuticals and things like that. So if you're connected to any of those systems, you are potentially contributing to those problems. If you use any kind of transportation, any kind of mechanical tractor or car or truck, or have your goods shipped anywhere, that's going to result in the release of air pollutants. And a lot of times people don't associate air pollutants with water pollution, right? But if you think about it, there's that old phrase, what goes up must come down. You ever hear about that when you're a kid? And then throw something up and it hits you in the head. All of that pollution eventually comes back down too, into our waters. And then finally, manufacture of consumer goods. Obviously, we've known about those water pollution issues for a long time. Those are the ones that we've been able to crack down on pretty well. But they still cause problems too. So basically, if this doesn't hit every single one of you, at least in some aspect, then maybe you need to think about our impacts a little more. Now, we do know water quality impairment is really widespread in the United States. It was the Clean Water Act that the main goal is to return all of the U.S. waters to swimmable, fishable conditions. Not necessarily to drinkable, they just wanted to get it to swimmable and fishable. So they set out, starting in the 1970s, to try to assess all the waters to see if they're good enough or not. As of today, this is the most recent data I could find from the EPA in 2017. Streams and rivers, of the miles that are assessed, it's over 1 million miles assessed in the U.S., 55% is listed as impaired. Only 45% is listed as good. And that's the best of all the categories. Lakes and ponds, they've assessed over 18 million acres of lakes and ponds in the U.S., 71% are impaired. Of the estuaries and bays, which is an important category in our region, 83% are impaired. And again, this is of the assessed ones. So this doesn't even count like everything that people haven't been able to look at yet. So right now we know that there's a pretty big issue in the United States. We often think of this as being a great country where we've done a lot of work for cleaning up stuff, but we still have these remaining issues. Here are the kind of top 3 pollutants in the top of this table, and then the top 3 sources of the pollution. Again, you have the 3 different categories. Rivers and streams, big 3 are siltation, pathogens, and nutrients. Lakes, ponds, and reservoirs, nutrients, metals, and siltation. Notice the siltation and nutrients are common. Estuaries, that's a little different. Pathogens, organic or enrichment, and metals. So those are a little bit different, but this one here, the low dissolved oxygen, organic enrichment, a lot of times that is a result of nutrient pollution. So again, we know nutrients are important in estuaries and bays too. Of the top 3, agriculture is high up, as is urban runoff and storm and sewers for the rivers, streams, lakes, and ponds. For the estuaries, we don't see agriculture here. We do see atmospheric deposition. That's a fancy term for saying what goes up must come down. Air pollution gets into the water. And also municipal point sources, so running off, or the wastewater treatment plants, construction, things like that. But right now, agriculture activities are responsible for about half of the impairments that we've found nationwide. So again, that's why we have the Agricultural Nutrient Management Program here in Maryland, to try to help reduce some of these issues that we see. So what are some of the consequences? This is actually an algal bloom that you can see from space. What they did is they took aerial photography and then overlaid a map over it so you could kind of see where the cities are. This is taken September 3rd, 2011. That's huge. You can literally see it from space. That's how pervasive this problem is. And algal blooms happen when you have nutrient pollution. When you get pulses of nutrients from large rainstorms, you get these algae grow, and they have a very quick lifespan, and they can grow really rapidly, and that's why you get these blooms. Here, this is actually a picture someone posted where they were driving through the algal bloom in their boat. Look at that water. It doesn't even look like water, does it? It almost just looks like they're driving through green paint. So these algal blooms can be a pretty serious issue. This is one from the Chesapeake Bay. This is an aerial photograph. This is down by Norfolk. But again, see the line there? You can see these algal blooms. So even here in our own region, we're seeing these issues.
What's that caused from again?
What's that?
What is that caused from?
Nutrients. Over-enrichment of nutrients. So what happens is nutrients get into the water, and again, something with like a really short, rapid lifespan, like algae, can grow really fast. And what happens is they grow really fast, you get these blooms. Unfortunately, they also die really fast, and then you get explosions of bacteria populations, which then eat all of the algae that's died, but then they take up all the oxygen out of the water, and we get these large dead zones every year. So this is a cyclical process that happens every year. In fact, they're predicting a really large one this summer because of all the spring rains and then crazy dry-off and heat that we've actually had this year. Now the other big issue, like we talked about, with nutrients, but also sedimentation. How many of you have ever seen a river that looks like this? Right? Everyone's seen the chocolate rivers right after a big rainstorm. This can be problematic too, because there's a lot of types of nutrients and metals and PCBs and crazy pollutants that can attach to these sediments and get in the water that way. So we have to take into consideration this too. So let's get into some of the basics. We have 2 types of pollution. You have point sources, which are very easily distinguished, and we kind of know exactly where they're coming from. Oftentimes we think of these as end of the pipe, right? Wastewater treatment plants, we know where that's coming from. Industry, we know where that's coming from. The thing is that those are the easiest to regulate. If you know where they're coming from, you can just tell those people not to do as much, right? So the Clean Water Act has been really good at regulating these. Now more recently, the confined animal feeding operations have been classified as point sources, because again, they're kind of known, you know, when large spills happen, that they come from that specific area. So they started regulating these as point sources, I believe. Am I right now? Yes? Okay, good. Now these non-point sources, this is where the problems have, still remain with the Clean Water Act. The Clean Water Act is not as good at regulating these. So these arise over a landscape. Think of them as like little things here and there. It's not that one person is fertilizing their lawn. They're not the ones that are causing the pollution of the bay. It's that everyone in the city is potentially fertilizing their lawn. So it's these little things that add up over the landscape that cause a bigger problem. So it's like, when it's kind of that mentality, like, I'm not causing the problem, everyone else is doing it too. Well, all of that adds up. So cropland and pastureland, fertilizing crops, can cause this. Towns and cities, that one car is leaking oil, that there's probably hundreds of other cars that are leaking little drops of oil. So all of these over time add up and cause problems. And these are the harder ones, like I said, to actually regulate. It's harder to know that it's that one person and not 20 other people that are doing the same thing. So our next clicker question: what types of pollutants are important for nutrients? Those point sources or those non-point? Or both? Or none? C, which is both of the above, 92% said. And that's what I would agree with, both of the above. So if you think about non-point sources, we just talked about that, right? Fertilizers, lawns, cropland, etc. But also think about human waste, right? That's a lot of nutrients right there. So those wastewater treatment plants, they've been getting cracked down on too with nutrient pollution. So they've been trying to add a lot of stuff as well. Back on the screen here. So let's get into the water cycle, because water is one of the more important aspects of how these nutrients are moving across our landscape, how they're being transported. So hopefully you guys all remember the water cycle. Yes, evaporation, transpiration, all that good stuff. So I'll go over it pretty quickly. But you have evaporation, which is when water turns from liquid phase to the gaseous phase. Transpiration is when plants do that, essentially. What do they call it for humans? What is it called when you turn your liquid into perspiration, right? Starting to do it a little bit here. It's nice and humid. But so evapotranspiration is kind of the combination of evaporation and transpiration. But the water's in a gaseous form. Condensation is when it turns back into a liquid form. Once all of those tiny small droplets combine to form a large enough droplet, we get precipitation. So whether it's rain or snow or ice. Now once it hits the land, that's where we start becoming concerned about nutrients. Because it can go one of two pathways. It can run off the surface, or it can infiltrate. And infiltrate is when it soaks down into the soil. So either way, it can carry nutrients with it. Once it soaks down into the soil, if it's going to go the infiltration route, it actually gets down to the point where all of the soil is saturated with water, and we call that our groundwater. And some people actually get their drinking water from that. So that's why that's of concern, because you don't want pollutants in there for your drinking water. Now the thing that be reminded about is that all of this is still connected. All the groundwater will feed lakes and rivers. So know that even if we have pollution in the groundwater, that's eventually going to make it to our rivers and streams as well. So all of this is connected. Now, not only do we have that going on, but you have different things happening at different seasons. So you have seasonality. In the summer, what we have is evapotranspiration, which is E plus T. You have rainfall, which is the R. Surface runoff is SR, and P is percolation, which is the same as infiltration. Now, the size of the arrow dictates how much of it is happening. So obviously in the summer, right, day like today, there's a lot of evapotranspiration happening. There's a lot of warm heat that's helping it evaporate. So that is going to be large. Percolation is going to be small. Surface runoff is going to be smaller than the other seasons. Because if there's a lot of evapotranspiration, there's not as much to run off or infiltrate, right? Now notice, along all of these different seasons, rainfall is approximately the same amount. So that arrow is about the same. The thing that's changing is these other three: evapotranspiration, percolation, and surface runoff. In the fall, notice evapotranspiration is decreased, but it's still there. Thus, percolation and surface runoff have increased. So this is when we start being concerned about water quality issues and what's happening in the field. In the winter, it's even worse though. Evapotranspiration is very, very little. There might be a little bit of evaporation happening, but there's not many plants growing in the winter, right? So there's not very much evapotranspiration. Thus, the percolation and the surface runoff are much greater at this point. So this is when we have to start considering what's happening with our nutrients. And to give you kind of another picture of how this changes over time and more of a local example, this is the soil water cycle on the eastern shore. What we have is in blue, it's precipitation averaged by month. What's interesting to me is that's actually the same, isn't it? Like, that's actually pretty steady. You always think of it being like really hot and dry in August, but actually, average speaking, we get about the same amount of water every month. There's some differences, but it's not like, out in Arizona or anything. The blackish line here, this is potential evapotranspiration. It's not necessarily the total that is happening, but it's the total that could possibly happen. So that increases as you go through the summer and then decreases into the winter, right? That should make sense. As you get more plants, there's more evapotranspiration. So then we have the two water things. We have the red, which is drainage. So this is the water that's going below the plant root zone. And then in this kind of, I don't know what that is, like a dark red, you have actual soil moisture. So again, in the winter, you have a lot more drainage and more soil moisture. In the summer, you see it decrease as that potential evapotranspiration comes up, right? So again, over time, you can see that you're not going to have as much drainage here or even soil moisture to worry about the nutrients running off. In the winter, though, yeah, it's going to be a little bit higher. So, review question. In what season is the risk of nutrient runoff loss the highest, due to runoff the highest? All right, most of you said winter, December, December through March. That is correct. That's when we gotta worry about nutrient runoff the most. Does anyone know when the winter restrictions for fertilizer application happens here in Maryland? It is December
15th.
Yeah, it's 15th, 16th. So again, the MDA is trying to use some scientific information in making these decisions. We know that these are when the runoff risks and the percolation risks are going to be the highest for nutrients. So this is one of the reasons why these restrictions actually exist. So I also wanted to show you not only does like the rainfall soil moisture change, but actually the nutrient concentration changes too. This is the nitrogen concentrations in the Pocomoke River during a 1-year period from January through December. And over here you see nitrate concentration from lower to higher. So see in the winter, they're high, they dip down in the summer, and then they increase as you go through the fall into the winter again. And again, this is because you don't have any plants growing in the winter, right? Taking up those nutrients in the river, whether it's actual like grasses or it's algae. Even algae does take up some of these nutrients. So you have high runoff risks, and that's why you get higher concentrations in the winter. So we have to think about how things are moving. You have your sources, whether it's animals, lawn fertilizers, whatever it is on your land, and you have to think about the various ways that it's moving, the nutrients are moving. So obviously you have surface runoff, we talked about that before, and this is actually, we're thinking about like the clear water running off when we talk about runoff. So this is nutrients that get dissolved in the rainwater and then flow over the surface. Erosion is more important for the nutrients that are attaching to particles, so the sediments. So this is when you're getting sediments moving off into the rivers. So again, they're both important, but they actually are slightly important for different kind of nutrients depending on the chemistry. The third thing you have going on here is leaching. Leaching is a term used for when something dissolves in water and moves with it down to the groundwater. So for instance, nitrogen. There's a form of nitrogen called nitrate that easily dissolves into water, and we call that leaching, nitrate leaching. So that can get into the groundwater, and then again, remember, groundwater is flowing, just like surface water is. Not nearly as fast. Surface water, I think they say like a rainfall that happens up in the like New York area of the Susquehanna River can actually take, days or a few weeks to get down to the Chesapeake Bay. But if you get a drop that goes into the groundwater, it might be hundreds of years, thousands of years, even 10,000 years before it actually makes it back out. So they take time, but they do slowly flow towards the surface water. Now, one other thing you got to think about is tile flow, especially out on the eastern shore. I know they use a lot of tile drainage. What happens is the stuff will leach, but then it goes into those pipes and it quickly goes back out to surface water, right? So it starts leaching, but then it gets into the tile and flows quickly out to surface water. So that's actually kind of accelerating how fast that nutrient or that pollutant would get to the water versus if it had gone down to the groundwater and then kind of slowly moved out. So these are all things you gotta think about, and we'll talk about these, kind of use these terms frequently throughout the next 2 days. So nitrogen and phosphorus. Nitrogen, the one that we're concerned about particularly, is nitrate. Nitrate, as I said, really likes to be dissolved in water. It dissolves pretty quickly. And it is a plant available form. So a lot of times it's going to be leached down to the groundwater. So oftentimes when we hear of groundwater contamination issues, if it's not like a pesticide or something like that, it's probably going to be nitrate. And unfortunately, this one can cause health concerns. Have you ever heard of blue baby syndrome? They say women who are pregnant or young children should not drink water with high nitrate concentrations, because it can actually, what happens is it binds with their blood instead of oxygen, and they literally suffocate. So that's why they call it blue baby syndrome, kind of a crazy thing. Now, remember though, if you have groundwater with high nitrate concentrations, that means that if it's feeding surface water, that can potentially have high nitrate concentrations too. So this one impacts both surface and groundwater. Phosphorus. Phosphorus doesn't like to be dissolved. It can be, so you will lose a little bit in some of the surface runoff if it dissolves. That's not a big contributor though. The biggest thing it likes to do is bind to sediment though. Phosphorus really likes to latch on to something. So when you start getting those big erosion events, especially after like a really heavy rainstorm, that's when you're going to see like big pulses of phosphorus getting into the water. So when we think of phosphorus, oftentimes we mostly think of it as more of a surface water issue, less of a groundwater issue. So nitrate can be both, phosphorus is more surface. This just kind of gives like a visual depiction of what I just talked about. So again, the size of the arrow kind of dictates how much of a issue this is or how much this happens. So with nitrogen, you see there's a gaseous form, either volatilization or denitrification. You'll learn about that coming up in the nutrient cycle section. But these are gaseous losses. And that's one thing we worry about with nitrogen, why you have to be careful about when you're putting it on or if you're putting it on the surface of the soil, because you want to avoid these gas losses. Plant uptake is important, obviously, but leaching and runoff and erosion can be issues with nitrogen. Now, with phosphorus, notice there's none of this gaseous loss here. Again, phosphorus prefers to be bound to something. It doesn't really go into gaseous form. So you get plant uptake, a little bit of leaching. Like I said, there's going to be some, because there will be some phosphorus that's soluble and can potentially move down, but it's not a big source. But the runoff and erosion are kind of the big issues with phosphorus. So some of the same things going on, like plant uptake and surface runoff, etc., but definitely different things going on with nitrogen and phosphorus. And I assume you will definitely be asked a question about that somewhere in the exam. So not only do you have to think about seasonality, you have to think about just the water cycle in general, but you have to think about just regular, normal, everyday stream flow versus storm flow. So everyday normal day flow is what we call base flow. You know how they've said it's going to rain for the last 3 days, but it hasn't actually rained for like a week and a half now? But the streams are still running, right? Where's that water coming from? Just magically appearing? Where's it coming from? Groundwater flow, right? So that's how these things actually, how these streams are actually still running, even though it hasn't rained and it's been god-awful hot. So we have to think about base flow. So remember, that's when we're going to see higher nitrogen concentrations. But then when you have storm flow, especially it seems like when we get rain lately, it's like this crazy amount of rain all at once. That's when you have to worry about what's called storm flow. And oftentimes we'll see kind of higher levels of phosphorus and nitrogen in both. So again, just to show you the difference between the two, this is a study. Trish, this one I wanted to ask you about. Where was this study done?
A watershed down in Anne Arundel County.
Okay, Anne Arundel. I was thinking
It
it
was
was
done by the group that's in the Science and Environmental Research Center.
Okay. So this, what they did is they looked at little watersheds that were in different land use areas. So one that was mostly forested, one that was had mostly pasture, one that was mostly cropland, and one that was mixed, a little bit of a mixed use between all of these. The blue is base flow. So again, they would go sample now when basically it was just the groundwater feeding the water, or the stream. And then they went and looked at storm flow, which is this orange. And again, we're looking at nitrogen levels here. So 2 things to note. One, Base flow levels of nitrogen tend to be lower. So storm flow, that's when you're going to see those pulses, the pulses of the nutrients. And then 2, what's going on with land use here? What has the highest? Pasture. I'd say cropland's pretty high up there too. Right? So again, some of the farm uses, we see some of these big issues. They don't have like urban suburban, so we can't compare those. But just to show you kind of these little landscapes that they looked at in Anne Arundel. You notice that in base flow, the nutrient levels are lower, storm flow, they're higher. But in something like a forest, which is used to the particular levels of nutrients we're using, that's going to be a lot lower than some of these other land uses that we see. So next question, the process of nutrient over-enrichment of a body, what is that actually called? Talked about it a couple times. All right, most of you said eutrophication, that's right. No one picked phosphorication, which is good because that's a word I think I made up. It might actually be a word, but. So eutrophication is correct. Nitrification is actually when nitrogen transforms from ammonia into nitrate. So you'll learn about that later. But eutrophication is the over-enrichment of nutrients. Now this is a natural process. This is something that's happened for a long time. There's always going to be nutrients washing off the land. It's just that we tend to accelerate it, with wastewater treatment plants and adding fertilizers that weren't naturally there, etc. So eutrophication is what we worry about in the bay. And even in our little lakes and rivers, etc., that we have around the state too. So they consider this to be one of our grand challenges in the 21st century, figuring out what's going on with eutrophication and trying to solve the issue. So again, this is why we have nutrient management, trying to help with the issue of the eutrophication in the bay. So generally speaking, what happens is you tend to have a healthy ecosystem, lots of underwater grasses, crabs, oysters, etc. And that's a balanced ecosystem. But when you get these constant storm pulses and excess nutrients added in, a couple things happen. You have the algal blooms. Algal blooms, like you saw how thick that one was with the boat driving through it, right? That actually blocks out sunlight for the underwater grasses. So that kills off the underwater grasses. Second thing is they multiply really rapidly, and then they die really rapidly. So you have the bacteria then that want to consume them, break them down further, decompose them. But the bacteria also have a very short lifespan, right? They grow rapidly too, trying to eat those bacteria. The problem is they use oxygen like you and I do. So they end up taking a lot of the oxygen out of the bay. And that makes the term is called hypoxia, which is lack of oxygen. If you get anoxia, which is completely no oxygen at all, that's even worse. But notice this, it tends to happen near the bottom because that's where all the algae have fallen down to. So unfortunately, if there were any grasses still surviving, they're not going to be there anymore. The oysters have to move out, or the crabs have to move out. Oysters don't do too well in that either. So you end up with something called the den zone, and this is happening in all of our major waterways, in all of our major ocean basins today, or all around the world. It's happening here in the Chesapeake. It happens in the Gulf of Mexico every year. All the major water basins, we're seeing this issue. So it is a kind of a big global issue too. Now let's talk about the Chesapeake Bay region specifically. Now the Chesapeake Bay is actually pretty unique. It covers, 6 states and the District of Columbia, so it's very large. Its average depth is only 21 feet. So it covers a huge land area, and it's actually fairly shallow. So it has kind of a small volume, if that makes sense. If you think about volume, like how much water is in this, that's volume. It has a very small volume, but it has a very large land area. So it has a ratio of watershed area to bay area at 14:1. The population is high, 17 million in 2010. Estimates in 2015 actually say it's over 18 million already. So it's not only already populated, heavily populated, it's getting more and more people. And that's causing more and more strain. Unfortunately, that's in direct conflict with the fisheries. Right now, they say the fisheries harvest is worth about $2 billion a year. I think I wrote that right. $2 billion a year. So obviously, all of the stuff that's getting into the bay is directly impacting the fisheries. And one of the major pollutant categories is nutrients, so the nitrogen and the phosphorus. Just to show you why I was talking about that watershed to water volume ratio is because, again, it makes the Chesapeake Bay very unique. Most places will have a lot or much less land space that's actually filling the bay. So the Gulf of Finland is the one that's closest to us, right? And it's less than 500 kilometers squared to kilometers cubed, versus we're up to almost, or like 2250. So you have a lot of land that's coming through a lot of forest and ag and people. All that water's coming through all those things before it even gets to the bay. And then we have a lot of interesting things going on with like our geology and our landscapes as well. So here, these are the different like types of bedrock, etc. in Maryland. And you can see there's a couple different zones. We'll talk about those regions. Now this actually shows a cross section. Say you took a section from this point down through the eastern shore, cut down into the ground, picked it up and looked at it like it was a sandwich. This is what you'd actually see. This is how the bedrock actually slants, and it all slants out towards the ocean. So what's kind of interesting is if there's pollutants up here, someone tapping into the ground, like going down that deep to get into the groundwater down here, might actually be accessing those pollutants that entered the groundwater system, hundreds of miles away. So again, like this all impacts further downstream, further down the aquifer, etc. So here are the physiographic provinces. This is kind of the areas of bedrock that the state is broken down to. And this all impacts the hydrology of the landscapes. So first is the Atlantic coastal plain. This has pretty thick soils. And it's going to be a little sandier, right, because this has been inundated by the ocean several times in the past million years. So you have more sand. Not to say that you don't have any clays and silts and heavy textures, because you do on the eastern shore. I don't know if any of you have experience with that or not. But there is going to be more sand than other areas of the state. Now notice this separation here. This is called the fall line. They call it the fall line because if you actually travel along this tends to be where the waterfalls in Maryland are. So like Rock State Park. I know there's one right in Baltimore County that I used to take my kids to. And this is because the Piedmont tends to be more resistant rock. So as the water streams go from resistant rock into less resistant rock, it actually erodes it away, so you get waterfalls then. But anyway, it's called the fall line. It's roughly around where 95 is. Now the Piedmont, like I said, it's going to have more resistant rock, so that means it's very thin soils. On average, they say the soils are only about 3 feet deep in this region. So it's definitely going to be different than the coastal plain. Going to be a lot more clay. Not to say that there's not sandy parts in the Piedmont, but a lot of the soils will tend to be finer textured. Blue Ridge, Ridge and Valley, Appalachian Plateaus, again thin, very rocky. I often hear stories about the crazy amount of rocks and fields in Washington County, for instance. So they're going to have a lot more areas of that. The one interesting thing is limestone and karst. Limestone is a rock that kind of gets easily dissolved by water. It's weird, it's very resistant unless it gets cracked. Once it gets cracks in it, then the water can move down through it and it kind of eventually build these caves and tunnel systems and things like that. So keep these in mind, because we're going to talk about soil textures when we talk about how water moves through soil. So if you think about the basic 3 textures, sand, silt, and clay, say you took a picture, blew it up 10 times. This is what sand would look like. Pretty big. Then you have silt, blow it up 10 times, it's much smaller. Then clay, they had to actually blow it up 1,000 times to kind of depict what it would look like under a microscope. So this is going to be much smaller even. So this is important when regards to water moving through these areas. Which one do you think would move faster through? The sand, right? I always like to use the example, if I was a crazy person and lit a fire in the back of the room and only one of these doors opened, versus if all of these doors open, which one would we get out faster? all the doors open, right? So you can think of me lighting the room on fire when you're thinking about water moving through soil for the exam. So again, not only do you have to think about pore space and textures, but also think about like how these things are kind of, how all these little particles are lined up to. In unconsolidated Atlantic coastal plains, you get a lot of rounded things. They're kind of lined up, but you get all these spaces between them. Places like the Ridge and Valley and the Piedmont, where you have more resistant rocks, what can happen is you get these fractures. And the fractures over time can get eroded. So you actually essentially build tunnels right to the groundwater, especially in karst areas. Has anyone ever seen a disappearing stream in a karst area? Yeah, one person here. They're it's kind of wild to see. I saw one, I did my graduate work in Minnesota, and we went and there's this huge stream bed, but apparently a cave had opened up underneath it. So you literally watched, I don't know, hundreds of cubic feet per second coming down and all of a sudden just disappearing right in front of your eyes. And it wasn't going across under the bridge. It was insane. So again, if you got something like that and you get pollutants in it and it gets into the groundwater, that can cause a serious problem too. So again, back to the bay. Let's talk about the specific issues. I kind of talked about the US issues. Let's talk about the bay specifically. Sources of nitrogen. Agriculture are these top three. You also have atmospheric deposition. That one always blows my mind. 20% of the pollution in the bay comes from air pollution. Isn't that crazy? And that's for nitrogen. We also have septic systems, developed lands, municipal wastewater. But agriculture, what is that? Something like 43% it makes up. 43% of nitrogen issues in the bay. Phosphorus, agriculture makes up 44%. Then you also have municipal wastewater. Again, we got a lot of phosphorus and nitrogen in our poop, so we got to deal with that. But also runoff, from our streets, from our lawns, etc. makes up a large portion too. And just because we've been talking about sediments in the past, I wanted to put that up. Again, agriculture is about 60%. Natural sources, I mean, there's always been sedimentation, right? For even before humans came along. But they think that would only make up about 20% of what we see in current day. Urban runoff is the other big one. And yes, all of these are regulated now. It's not just agriculture. But let's look at the price tag for these. And this is something that kind of struck me. Say you want to reduce nitrogen pollution by 1 pound. This is how much it would cost by doing various different practices. Restore a wetland, $1.50 to reduce 1 pound of nitrogen. It's not too bad. Add a grass bufferway to a farm or do conservation tillage is going to cost $3.20 for 1 pound of nitrogen reduction. Cover crops, $4.70. These are going to be the cheaper four. Do a wastewater treatment plant upgrade, just a normal upgrade, that's going to cost $15.80 per pound. Enhanced nutrient management is going to cost $21.90. This is doing like precision ag and all those cool things. Wastewater treatment plant upgrades, the big multi-billion-dollar upgrades they're doing. I know they're doing a big one up in Baltimore. Those kinds of things are going to cost a lot, $47.40. But just stormwater management, look how expensive this is. Just doing it in a place that isn't even constructed yet. New construction is $92.40 per 1 pound of nitrogen reduced. Stormwater retrofits, going into an old community that didn't have anything to begin with, that's going to cost over $200. So again, this is kind of why there's a lot of focus on agriculture, because we get more bang for our buck. The more money we spend in this area, the more reductions we actually see versus you only get a little bang for your buck when you're doing stormwater retrofits. And they are doing these, but it costs a lot more to get just as much reduction. So that's why we're working with agriculture to try to reduce nutrient issues. So this is actually part of the TMDL, working with trying to reduce nutrient pollution, which is one of the big issues in the Chesapeake Bay. So let's talk about that nutrient balance. What do you think a nutrient balance is? All right. Not quite as certain as the other answers, but 60% said inputs versus the outputs. And 26% said NMP input should equal crop uptake. It is actually C for this one. When we're talking about a nutrient balance, this is when people are looking at the inputs of the farm So the nutrients that they're bringing off or from off farm to the farm versus how many nutrients are leaving in the crops or milk products or whatever it is. So what's coming in versus what's going out. So traditionally, and some small farms kind of had more of a closed system. And it doesn't mean there weren't any inputs or outputs, but those inputs and outputs are a little more balanced. So what you have is you have your soil that provides the nutrients, etc., for your crops. You get your crop, and you have to potentially put a little bit of nutrients on, NPK. You get your crop, use that crop to feed your animals. Animals produce a product, so some of that goes off the farm. About a quarter of the nutrients leaves there, but about 3/4 of the nutrients is in the manure. And then that gets recycled back to your soil, which provides a lot of the nutrients. So again, you only have to add a little bit, whatever you need a balance of. So this one is a little more, like I said, closed loop. Everything's staying on the farm. You have a little bit coming in and a little bit leaving. Now, again, this is more of what we consider to be a local system. But in the U.S., we've moved kind of to have specialized areas, right? The Midwest, they grow a lot of the grain crops. So those grain crops are going to feed animals, but the animals aren't greatly in the Midwest anymore. Now, Colorado, there's a lot here in the Eastern Shore. So then those crops get sent somewhere else, another region of the U.S. So again, quarter for like the chicken farm, quarter of the nutrients go off in the chickens, 3/4 are left in the manure. But the manure doesn't get shipped back to Iowa, right? It stays here. So all the nutrients that are getting put into our crops and leaving those farms comes here and it doesn't leave here, except for a tiny amount. So that's where we're getting an imbalance. There's actually been some interesting studies looking at like these nutrient balances and how farmers can adjust things so that it makes more kind of cost sense for them. So this is one of the issues that we've seen, right? We get all these nutrients coming into the bay, but not a lot of them are leaving. And that's why we've gotten excess nutrients in our soils. So if you want to just look at it another way, you can actually do case studies with your farmers. Try to look at all the different inputs. What do you got coming in your feed? Yeah, even the feed has nutrients, right, for the animals. You got to think about that. What fertilizers are you putting in that are coming from off farm? You got any legumes, soybeans? What kind of nutrients are they adding? That's technically an input. And then even look at rainfall. Like I said, what goes up must come down. If you analyze your nitrogen in the rainfall, you actually see there's a fair amount in there too. So that's adding to the system coming from off farm. If you have a balanced system, what's coming off in your animal products and your crops would hopefully kind of equal out these inputs. But if not, that's when you start seeing greater and greater losses. And losses can come in a variety of ways. The nutrient losses that we talked about, the gaseous losses, the surface runoff, etc. So those, again, you have to think about that. Technically, it's kind of lost money, right? You don't want to actually lose nutrients. You need nutrients on your farm. So that's what we're talking about when we talk about nutrients. So how do we reduce some of these ag-related nutrient issues? Have you guys heard of the 4 R's? Right rate, right source, right time, right place. Fertilizer management, same goes with manure. If you get it on at the right time and right place, you're less likely to get losses. If we are supposed to get the amount of rain we're supposed to get today, you probably didn't want to go put a bunch of manure on the ground because a lot of that's going to run off. So trying to avoid big rainstorms when you're applying manure, for instance, would be important. But also know if you already have areas where you have issues, like high phosphorus soils, probably don't want to be applying very much more phosphorus there because you're just losing your money. It's just going to leave the system. So another thing we like to think about is kind of your economic yield. Have you ever heard of this? Where you're not always, like for a long time, we just always wanted to get the best yield that you could, regardless of how much it cost to get there. Well now, when fertilizer costs more money, all that stuff, that's eaten into your profit. So if you look at the economic return on your yields, that's kind of trying to balance out your inputs versus how much you're getting for that crop. So say here we have nitrogen in pounds per acre, so 50 through 400, and then your yield, which is percent of maximum, up to 100% yield. So say you had a low amount of soil nitrogen in the soil, you had 40 pounds of nitrogen. That's going to get you a pretty nice yield bump, about 16% increase in yield. Is that worth it economically? I mean, we don't have the prices, but probably, yeah, right? That's probably going to be worth it then. But say you had high nitrogen levels or whatever in your field already, you're up to this 150 pound per acre thing, you add an additional 40 pounds, you're only going to get a 2.5% yield increase. Is that worth it? Maybe not. Depends on how much fertilizer costs, right? So again, a lot of farmers are starting to think about this stuff. Does it make sense to add that additional unit of nitrogen financially, only get a tiny little bit of yield? But if it bumps your yield a good bit, obviously, it's something you want to consider. The other thing to think about is how much is left in the soil, and a lot of studies have looked at this. In the pink here, you have fall soil nitrate. In the, I guess it's blue, but it looks black here. This is your grain yield. So what would be your yield that you'd aim for here to reduce how much soil nitrate you have left over? What do you think? I heard someone say 160. I'm going to say 150 just because that's one of our data points there. But yeah. So think about it again here. They got a tiny little bump in yield, right? But is it worth wasting all that money on nitrogen that's possibly going to run off or leach out over the winter? Does it make sense? Remember, anytime that nitrogen is lost from your field, that's money. That's money you lost because you paid to put it down. So kind of think about that in that regards. And a lot of people are starting to do this. Some of the BMPs, I'm sure most of you seems like you have some sort of ag background in here, so I'm sure you've heard a lot of these before, so I'll just do a quick review. But for cropland, using field buffers, this is actually required here in Maryland now, right? For ag lands, you cannot apply nutrients within 10 feet of a body of water. Try that again. So that's actually something that's required here. But the bigger the buffer, the more likely you're going to get an impact. No-till or conservation tillage, they actually just started allowing this right here in Maryland. Before, if you applied manure, you had to incorporate it regardless if you did no-till. But now they're allowing exemptions for no-till, so you don't have to necessarily plow the manure under. Because this is beneficial. When you have stuff on the surface of the soil, you're going to have less runoff and less erosion. So that helps reduce nutrients. Cover crops. I have a special soft spot in my cover crops. I did cover crop research. Doing great in Maryland. In Minnesota, they're not doing so well with cover crops, but they had a record-breaking year this past year with the cover crop cost share program here in Maryland. So this is actually something that a lot of people are looking into. Again, if you have something on the surface, that's going to reduce erosion. And then proper use of fertilizer, again, that comes back to those 4 R's. Put it down at the right rate, the right source, the right time, the right place. For livestock, stream exclusion, again, I believe that's required in Maryland. You're allowed to have stream crossings, but you're supposed to have the animals out of the stream otherwise. For manure management, you have to have proper storage methods. If you want to stack your manure here in Maryland, it has to be removed within a year, and you have to allow that to grow back into cover. You can't let it just kind of sit there for a decade and say that it's composting. They don't let that fly anymore. Forested buffers are even better than just grass buffers. Again, trees. Can you imagine like how much water a tree has to take up? That's a lot of water. So again, that can reduce evapotranspiration or increase evapotranspiration, which reduces surface runoff. And also rotational grazing. Have you all heard of rotational grazing? Very small plots, allow the animals on for a few days, or maybe 24 to 48 hours at a time, and move them on so they don't erode the land too much with compaction, etc. But it allows kind of the areas to rejuvenate. Sometimes they like to congregate around the same area, and you always see like denuded areas, etc. All right, last question for this little module. Which of the following field scenarios would you consider environmentally sensitive, which would benefit from a cover crop? All right, most of you said all of the above, and that is correct. Definitely, remember karst underlying a field. That's going to be where you're getting those underwater, or those caves that essentially form. If you get water in those, you just flush right to the groundwater pretty quick. Coarse textured soils, high sand, again, water's going to move quickly down to the groundwater. You got to worry about those. And places where you have high soil phosphorus. Remember, once the phosphorus gets higher and higher, that means a little bit more of it's going to be in solution. So that means more of it can run off or erode, etc. So that's why all of the above is correct. So I believe that's the last one. Do we have any questions on this?